In the annals of aviation history, few events have captured global attention and sparked as much concern as the worldwide grounding of the Boeing 737 MAX.
For nearly 2 years, one of the world's most anticipated new aircraft sat idle, an extraordinary measure taken after 2 tragic crashes claimed 346 lives. This wasn't just a technical glitch, it was a crisis of trust, a cascade of errors, and a moment that forced the entire industry to re-evaluate its commitment to safety. We'll explore the complex story of how a single software system led to a global halt in air travel.
To understand the grounding, we must first understand the aircraft itself.
The 737 MAX was Boeing's answer to the challenge posed by its competitor, Airbus, and their fuel-efficient A320neo. Boeing needed to upgrade its incredibly popular 737, a design dating back to the 1960s, to incorporate more modern, larger, and more fuel-efficient engines.
The challenge?
Fitting these bigger engines onto a relatively low-slung airframe. This design decision had subtle but significant aerodynamic consequences that would ultimately require an electronic intervention. To compensate for the aerodynamic changes caused by the larger engines, Boeing introduced a system called MCAS, the Maneuvering Characteristics Augmentation System.
Its purpose was to automatically push the aircraft's nose down if it detected that the plane was climbing too steeply, too fast, and risked a stall.
A stall occurs when the wings lose too much lift to keep the aircraft in the air, a critical situation in flight. MCAS was designed to operate quietly in the background, making the MAX feel like previous 737 models, and pilots were given very little information about its existence or operation. The first tragedy struck on October 29, 2018. Lion Air Flight 610, a brand new 737 MAX, crashed into the Java Sea shortly after taking off from Jakarta, Indonesia. All 189 people on board perished. Investigators quickly identified erratic airspeed readings and a struggle between the pilots and an automatic system trying to push the nose down.
The aircraft's angle of attack, or AOA, sensor was found to be faulty, feeding incorrect data to MCAS. Unbeknownst to the crew, this system was repeatedly driving the nose down, despite their efforts to pull it up. Just 5 months later, on March 10, 2019, tragedy struck again. Ethiopian Airlines Flight 302, another 737 MAX, crashed 6 minutes after departing Addis Ababa, Ethiopia, killing all 157 passengers and crew. The flight profile bore chilling similarities to the Lion Air accident, an immediate struggle after takeoff, erratic pitch movements, and the aircraft's nose being pushed down.
The striking similarities between the two crashes, both involving brand new 737 MAX aircraft shortly after takeoff, signaled to the world that something was fundamentally wrong with the aircraft's design, leading to immediate and widespread alarm. Following the Ethiopian Airlines crash, countries around the world, one by one, began to ground their 737 MAX fleets. This was a remarkable and rapid sequence of events, with aviation authorities from China, Europe, and other nations acting swiftly, often before the United States Federal Aviation Administration, or FAA, issued its own grounding order. By March 13, the FAA, facing immense international pressure and mounting evidence, ordered the grounding of all Boeing 737 MAX aircraft in U.S. airspace. This unprecedented global consensus effectively brought a halt to one of the most prominent passenger jets. Investigations revealed the core issue. MCAS, the Maneuvering Characteristics Augmentation System, relied on input from a single angle of attack sensor. If this one sensor malfunctioned and sent erroneous data, indicating the nose was too high when it wasn't, MCAS would repeatedly activate, pushing the nose down. Furthermore, pilots were not adequately trained on MCAS or how to effectively counter its persistent commands in an emergency. This single point of failure, coupled with insufficient pilot awareness and a complex override procedure, created a deadly scenario in both accidents. Faced with an unprecedented crisis, Boeing embarked on a massive effort to fix the 737 MAX. The primary focus was a comprehensive software update to MCAS. The updated system now takes input from 2 angle of attack sensors, cross-referencing their data. If there's a significant disagreement between the sensors, MCAS will not activate. Additionally, MCAS can now only activate once per AOA event, preventing repeated nose-down commands, and its power is limited. Boeing also developed new training materials to ensure pilots fully understood the system and how to respond to potential malfunctions. The return of the 737 MAX to service was a long, arduous process, demanding rigorous scrutiny from aviation authorities worldwide. The FAA, EASA, and other regulatory bodies conducted their own independent reviews, test flights, and evaluations of Boeing's software fixes and training protocols. Pilots underwent mandatory simulator training, focusing specifically on MCAS scenarios and emergency procedures. This painstaking recertification aimed not only to ensure the aircraft's safety but also to restore public trust, a critical step for an industry that relies entirely on confidence. The Boeing 737 MAX grounding was a profound, expensive, and ultimately tragic lesson for the aviation industry. It highlighted critical vulnerabilities in aircraft design, software certification processes, and pilot training. The crisis led to increased scrutiny, calls for greater transparency, and a renewed emphasis on international cooperation in aviation safety standards. While the MAX is now safely back in service, its story serves as a permanent reminder that in aviation, every detail matters, and the pursuit of safety must always override commercial pressures. It has irrevocably changed how aircraft are designed, certified, and regulated.